Welcome to today's deep dive. We are looking at a really brilliant technical blog post today titled The Secret Life of Python Multi-Region Failover.
Yeah, that's by Aaron Rose from the tech-reader blog. It's a great piece.
It really is. And our mission for you on this deep dive is to, well, basically explore how applications survive massive catastrophic cloud outages.
Right, the real nightmare scenarios.
Exactly. We are going to look at the raw mechanics of how a system transforms from this fragile, localized setup into an invincible, continent-spanning architecture.
Because if you work in tech, or honestly, even if you just rely on tech to run your business, which is everyone at this point, you really need to understand the physical realities of what actually keeps the lights on when things go catastrophically wrong.
Yeah, so we don't really think about it. We just expect it to work.
What's fascinating here is how we often assume the cloud is this magical, omnipresent safety net. We treat it like an abstract concept, like a vapor that just exists everywhere at once.
But it's literally a cloud in the sky.
Exactly. But the cloud is just someone else's computer. I mean, it is tied to physical buildings. And physical buildings catch on fire.
Right.
They lose power. Their cooling systems fail. Or, a construction crew accidentally slices through a main fiber optic trunk down the street.
Which happens way more often than people think. And that brings us to the vivid framing device the author uses to ground this massive technical concept.
Yeah, the library scene. I love this.
It's so good. So we're introduced to two characters. You have Margaret, who is this seasoned, battle-tested senior software engineer, and Timothy, her junior colleague.
The quintessential confident junior developer.
Totally. And the author places them in this grand, quiet, Victorian library in London. It's an environment where code quality and craftsmanship feel like the most important things in the world.
Right. It's this pristine, highly logical mood that contrasts perfectly with the messy physical reality we're about to dive into.
It's a great narrative anchor. We see Timothy leaning back in his chair, sipping his coffee, radiating that undeniable air of satisfaction.
Oh, yeah. He just finished a big deployment, and he believes his system is completely bulletproof.
Okay, let's unpack this setup, because Timothy hasn't just, thrown some sloppy code over the wall. He has actually built a very robust architecture on paper.
He really has. I mean, he has fully decoupled his system.
Right. He has protected his API limits. He's locked his database secrets away in a secure vault, and he has set up dead letter queues.
Yes, so that if any message processing fails, it gets safely caught and stored for later review. He's applied almost every best practice you would expect for a single region deployment.
He's checking all the boxes. He even boldly tells Margaret that if their third-party payment vendor goes offline for a month, his system will queue everything up perfectly.
Yeah, he says they won't lose a single byte of data. He actually calls his architecture invincible.
But he is completely missing the macro-level threat. Reading his dialogue, it struck me Timothy essentially built a house with a state-of-the-art security system.
Okay, I like where this is going.
Right. He's got vaulted doors, reinforced windows, backup generators in the basement. But he completely forgot to consider what happens if the entire neighborhood floods.
Yes, exactly. It doesn't matter how many internal redundancies you have. If the primary location is underwater, the house is gone.
And Margaret, being the senior engineer, she sees this immediately. The article describes her giving him this silent, single eyebrow raise reaction.
The classic senior engineer stare.
Right. And she acknowledges his impressive single-region architecture, which is, a very polite, subtle dig.
Very subtle.
And then she drops the ultimate hypothetical on him. She asks, what happens if us East 1 goes down?
And Timothy laughs. He literally chuckles at her and says, the primary AWS data center in Northern Virginia, it never goes down.
Which is just famous last words.
Oh, completely. If we connect this to the bigger picture, Timothy's hubris is basically a rite of passage. Almost every engineering team shares this blind spot until they experience their first catastrophic infrastructure outage. The reality of US East 1, which is the primary Amazon Web Services region in Northern Virginia, is that it is the beating heart for a massive portion of the internet.
It's huge.
And historically speaking, when US East 1 experiences a massive networking event or a cascading power failure, half the internet crashes with it.
Like Ring doorbells stop working, massive streaming services go dark, banking APIs time out. The blast radius is enormous.
It's wild. And Margaret forces Timothy to confront that stark reality. All of his beautiful safety nets, His meticulously configured API gateways, his optimized Lambda functions, they simply cease to exist if the physical building in Virginia goes offline.
The state-of-the-art internal engine sensors don't matter if the engine itself has been destroyed.
Exactly. So to achieve true enterprise-grade resilience, Margaret explains that your architecture cannot physically exist in just one location. It has to span the continent.
So the discussion naturally shifts to her solution. They need to implement multi-region failover. They need to stretch their architecture all the way over to US West 2, which is the AWS region in Oregon.
But this introduces a massive technical hurdle. When teams first look at disaster recovery, they tend to focus on the compute layer, right?
Right. The Lambda functions, the containers, the actual executing code.
Yeah.
Wait, I have to stop you there because this is where the mental model usually breaks down for me and probably for a lot of people listening.
Okay, let's hear it.
If everything is just infrastructure as code these days, why can't we just instantly deploy our Lambda functions to Oregon in a matter of seconds? Like we push a button, the code spins up on the West Coast, and we are back online. Why is this actually a hard problem to solve?
That's the trap.
Huh.
Because the compute layer is disposable. The compute layer is not the business. It just runs the business.
Okay.
The hardest part of a multi-region strategy is the state, the data.
Ah, the data.
Yes. If a user's shopping cart data or their session token or their payment history is physically trapped in a dark, powerless data center in Virginia, spinning up fresh compute resources in Oregon is entirely useless.
Oh, wow. Yeah, because you essentially have a brand new, completely empty application.
Exactly. The user logs in and their entire profile is gone. The state of your business is erased until Virginia comes back online.
So the code is running, but it has no idea who anyone is or what they're doing.
Precisely. You need a mechanism to ensure that the data living in Virginia is constantly, reliably mirrored in Oregon,
Yeah.
just waiting for a disaster.
And that's where Margaret introduces the first key piece of technology to solve this, right? DynamoDB Global Tables.
Yes, DynamoDB Global Tables.
Let's get into the mechanics of this, because the way Margaret implements it in the code base is surprisingly elegant.
It really is.
She opens up Timothy's AWS Cloud Development Kit stack, his CDK stack. And instead of rewriting his entire database architecture, she goes to his existing DynamoDB table definition and simply adds a single configuration property called replication regions.
And she passes in the Oregon region. Just like that.
One line of code.
That one line of code transforms a standard localized database table into a multi-region entity. Under the hood, AWS handles the heavy lifting of data synchronization. But the way it does this is crucial to understand.
Right, it's asynchronous, isn't it?
Exactly. It uses asynchronous replication.
Let's expand on that asynchronous part, because it's the core of how this actually works without breaking the user experience.
Sure.
If a customer in New York adds an item to their cart, that request hits the Virginia database. Now, if the database was using synchronous replication, Virginia would have to pause, send that data 3,000 miles across the country to Oregon, wait for Oregon to confirm it, save the data, and only then tell the customer in New York, okay, your item is in the cart.
Which would introduce massive latency. You'd be fighting the literal speed of light.
Right. It takes physical time for light to travel down a fiber optic cable to Oregon and back.
It does. The checkout process would feel incredibly sluggish. People would abandon their carts. So asynchronous replication solves this.
How so?
Virginia immediately confirms the right to the customer in New York, keeping the application lightning fast. Then, milliseconds later, in the background, AWS natively replicates that exact record across its internal fiber backbone to Oregon.
The article notes this replication typically happens with a latency of under 1 second.
Yes, under a second.
Less than a second to mirror a production database across an entire continent. That's just wild to me.
It is a profound piece of engineering. But Timothy, looking at this architectural upgrade, immediately zeroes in on the business reality.
Oh, right. The cost.
Yep. He points out to Margaret that running a constantly synchronizing copy of your database in a second region must carry a significant premium on their AWS bill.
Because it essentially doubles the storage costs, plus you have to pay for all that cross-region data transfer.
Exactly. But Margaret frames it entirely around ROI, the return on investment. She asks him to weigh that monthly database premium against the catastrophic financial and reputational cost of a 16-hour total business outage.
I mean, when you frame it that way, the premium is negligible.
Completely negligible. When Virginia goes dark, Oregon has an exact up-to-the-second copy of your entire business. Which brings us to the first major metric of disaster recovery, RPO.
RPO, or recovery point objective. So we are looking at RPO, which is basically asking, in a worst-case scenario, How much customer data are we willing to just write off as gone forever?
Right.
If your RPO is 24 hours, you are telling the business you are okay with losing an entire day's worth of transactions.
Which for most modern businesses is unacceptable. But thanks to the under 1 second asynchronous replication of global tables, Margaret and Timothy's architecture achieves an RPO of near zero.
Zero. That's incredible.
Yeah. If a catastrophic event takes out the Virginia data center instantly, the absolute maximum amount of data they lose is whatever was written in that tiny sub-second window before it could be replicated to Oregon.
Everything else is safely waiting on the West Coast. Okay, so we've solved the state problem, the database is synced, and Margaret deploys an identical CDK stack to Oregon, so the Lambda functions and API gateways are sitting there, fully configured. But we have a glaring routing problem now.
We do.
Let's think about this logically. Say we run a highly successful grocery store in Virginia. We realize the flood risk, so we build an identical, fully stocked backup grocery store all the way across the country in Oregon.
Okay. The shelves are stocked, the cashiers are at the registers, everything is perfectly mirrored.
But the customer's browser, think of it as their car is hard-coded to drive to the Virginia store. When US East 1 goes down, the customer's browser doesn't magically know that Oregon exists.
Right, it just drives straight into the floodwaters.
Exactly. It drives into the floodwaters, times out, and displays a massive error page. Having a backup store is completely useless if the traffic continues to route into a black hole. So how do we instantly drop a detour sign and reroute internet traffic when the disaster strikes?
Timothy actually maps this exact dilemma out. He's like, how do you physically hijack the customer's browser request mid-flight?
Right.
And Margaret introduces the final piece of the puzzle, Amazon Route 53. She refers to it as the Internet's traffic cop.
Route 53 is AWS's highly available DNS web service. But they aren't just using it to map a domain name to an IP address here, are they?
No, they are using a specific active feature, a Route 53 health check combined with a DNS failover routing policy.
The mechanics of this health check are fascinating.
They really are. Route 53 deploys a fleet of checkers located around the world. Every few seconds, these checkers send a request to the primary Virginia API. They are constantly asking the system, are you returning a healthy 200 OK status code?
Here's where it gets really interesting. As long as that health check returns a healthy status, Route 53 continues to resolve the domain name to the Virginia infrastructure. Traffic flows normally.
Right.
But Margaret configures a strict threshold. 3 strikes. If the health check fails 3 times in a row, Route 53 automatically executes the failover.
It stops returning the IP address for Virginia and instantly starts returning the IP address for the standby API in Oregon.
It automatically flips the switch.
And that lack of human intervention is paramount. Think about it. During a major regional outage, engineering dashboards are failing, alarms are screaming, executives are panicking.
It's chaos.
Complete chaos. You cannot rely on an engineer to manually log in, diagnose the issue, and manually change a DNS record.
No way. The system has to self-heal. But there is a hidden trap here that Margaret has to account for, right? Even if Route 53 changes the IP address record, client browsers and local internet service providers cache DNS lookups to save time.
Yes, the TTL.
Right, this is the PTL, or time to live.
This is such a critical detail. If Timothy had left the DNS TTL set to, say, 24 hours, Route 53 could flip the switch to Oregon all at once, but a user's laptop in Chicago would still say, I already looked up this domain this morning, I know it lives in Virginia.
And it would keep driving into the floodwaters.
Exactly. It wouldn't even ask Route 53 for the new address.
So Margaret sets the TTL incredibly low, maybe 60 seconds. This forces the customer's browser to constantly ask Route 53 for directions.
Yes. So when the 3 health checks fail, and Route 53 flips the switch, the browser asks for directions, gets the new Oregon IP address, and immediately reroutes.
Let's connect the entire sequence here because it's beautiful.
Right.
The Virginia data center loses power.
Good.
The Route 53 health checkers fail 3 times.
Yes.
The DNS record updates. The customer's browser, thanks to the low TTL, gets the new Oregon address.
Right.
The very next time the customer clicks checkout, their request hits the standby API in Oregon.
And because the DynamoDB global table asynchronously replicated their shopping cart data just milliseconds before Virginia went dark, Oregon reads the database, finds the cart, and processes the order.
0 data loss.
0 data loss. The only difference the user might notice is like a slight bump in network latency simply because the physical distance their data packets are traveling has changed.
But the application stays online. It remains fully functional while competitor sites who are stuck in a single region are completely down.
Which is a massive competitive advantage. And this brings us to the second major disaster recovery metric Margaret introduces to Timothy, RTO.
RTO, or recovery time objective. So if RPO is about data loss, RTO is about downtime.
Exactly. RTO measures the maximum acceptable amount of time your application can be offline before the business suffers irreversible damage.
Right.
Because Route 53 is automatically detecting the failure and flipping the DNS switch without human intervention, their RTO shrinks from potentially hours to just a few minutes.
Right.
Literally just the exact time it takes for the health checks to fail and the brief DNS TTL to expire.
Shrinking a multi-hour regional blackout into a 3-minute hiccup is an unbelievable engineering achievement.
It really is.
Now, Margaret defines this specific architectural pattern they've built as an active-passive setup.
Yes. In an active-passive architecture, the primary region, Virginia, is the active environment. It serves 100% of the live customer traffic.
Oh, wow.
The secondary region, Oregon, is entirely passive. The compute layer there sits idle. The Lambda functions are deployed but dormant, simply waiting.
It's a hot standby. The database is actively receiving the replicated data, keeping the state perfectly matched. But the application servers in Oregon are basically twiddling their thumbs until Route 53 pulls them off the bench.
That's a great way to put it. It is incredibly robust, and it keeps costs lower than running two fully scaled environments simultaneously.
Yeah, that makes sense.
The article ends with Timothy updating his architecture diagram. He draws this thick, solid line connecting his resources on the East Coast to his resources on the West Coast.
So what does this all mean? We started with Timothy's localized fortress, that incredibly secure, heavily monitored system that was completely blind to the fact that the actual building it lived in was a single point of failure.
Right.
And through Margaret's guidance, we watched that system evolve into a continent-spanning, self-healing architecture.
It represents a fundamental shift in how an engineer views the cloud. You stop protecting the application from just software bugs, and you start protecting it from the physical, chaotic realities of the world.
And this is universally relevant for you listening. Whether you are a software engineer deep in the trenches, actively writing CDK stacks and configuring TTL values on DNS records, or if you are a product manager or an executive planning for business continuity.
Oh, absolutely.
Understanding the real-world trade-offs here is vital. Weighing the premium costs of running a DynamoDB global table against the catastrophic revenue loss of a 16-hour business outage is not just an engineering optimization, it is a core business survival skill.
This raises an important question regarding how companies scale. The core of true enterprise resilience is always a balancing act.
How so?
Well, you are constantly balancing your RPO, how much data you can afford to lose, and your RTO, how long you can afford to be offline, against the sheer financial cost and the immense engineering complexity required to achieve those numbers.
Right. You can't just mandate zero downtime, zero data loss in a vacuum. It doesn't work like that.
No, achieving those metrics requires serious architectural discipline, the kind Margaret demonstrated by combining global tables with automated health checks and intelligent DNS routing.
It's layers of defense.
Exactly. Every extra 9 of reliability moving from 99.9% uptime to 99.99% exponentially increases the complexity of the system.
Which leads perfectly into a final thought I want to leave you with to mull over. We spent this entire deep dive looking at an active-passive setup. Oregon patiently waits as a backup.
Right.
But imagine the sheer complexity of moving to the holy grail of high availability and active setup.
Oh, man.
Imagine a scenario where users on the East Coast and users on the West Coast are actively writing data to the same database simultaneously, and both regions are serving live traffic.
That is where the physics of distributed systems truly breaks people's brains.
It really does. Think about the conflict resolution. If a user in New York and a user in Los Angeles both try to book the exact same airline seat or update the exact same inventory count at the exact same millisecond, how does the cloud decide who wins?
That's the million-dollar question.
When data is flying across the country in both directions, relying on timestamps isn't enough because server clocks drift. You get into vector clocks, last writer wins algorithms, and split-brain scenarios.
Resolving those conflicts without breaking the system or corrupting the data is a whole different level of engineering magic.
It forces engineers to fundamentally rethink how data consistency works.
It absolutely does. It's a massive leap in complexity.
It really is. Next time you load up a web application and everything works perfectly, take a moment to appreciate the invisible safety nets spanning the continent to keep that experience seamless. Thank you for joining us on this deep dive.